Pay attention. Go. I'm on page 70 and you should be too. Ready?
Wait, can we do one question of?
No, not now that I'm started, sorry.
Okay. Good.
Section 2.2 is called limits involving infinity. Sounds scary, but it isn't. It's easy. But you gotta get the concept in your head. If you don't get the concept, I mean, then it can be tough. We're going to consider a couple of functions that are the easiest ones to demonstrate what's going on. The first one we're going to consider is f of x equals 1 over x. That is the parent function for all rationals, all rational functions. And I don't know if you remember what it looks like, but it looks like this. It will cross at the point 1, 1, and -1, -1, and have branches that treat the axes as asymptotes. You can graph it on your calculator if you want, but that's what you're going to get. Looks like that. And so the domain restricts x equals 0, and the range restricts it on y equals 0. It's the only places on the graph where it never hits. It also, so there are no x or y intercepts on it, just to note. Now, we talked about limits yesterday. If this is the function I'm considering, well, actually, any function, but we're going to use this as an example. If I say, what's the limit as x goes way, way the heck out to the right of this function, any function actually, of this one right here, I guess I better stay specific to this for just a minute. But that limit is 0 because what you're asking is, as we let x go way out to the right, what's the function doing? What are the function values going to? And the answer is 0. Remember, when we're talking about a limit, we don't care what happens at infinity. Just as we approach it, we're getting closer to 0. It never hits it, never touches it, but it gets closer and closer and closer to 0, and that's what this is asking, right? Okay, so very same thing happens if I ask what's the limit as x approaches negative infinity. What's that?
0.
Negative infinity is also 0. But if we go right, it approaches 0 from above. If we go left, it approaches from below, but we don't care about that. Just what's it settling on? That's all we're asking. Okay, so we could say, since these are the same number, in this case, we could say, and we could summarize it this way, that x approaches infinity, positive or negative infinity. Since it's the same thing, you can lump them together. Okay? That's just kind of notation, how we handle that. But if you've got another function, and there is one, we'll take a look at it in just a minute. But if the graph of it looks like this, comes down here, maybe goes through the origin, maybe not, probably. Anyway, goes like that. So that this line right here is an asymptote, and this line right here is an asymptote. Pretend I actually got close to that. And this location on the y-axis is B. And this location on the y-axis down here is, no, they don't have to be the same. I don't want you to get that impression. Q. Then if this is the function f of x, let's make it g so we don't get confused with this one. This is the function g of x. And we say this about it. The limit as x approaches infinity of g of x is b. Yeah? And the limit as x approaches negative infinity of g of x is q. So we don't have that option to lump them together here because they're not the same thing. And so we have to indicate which direction we're headed and where the y values are settling. And that's kind of what you're seeing to the left on page 70 in the left column. Here's what we say then. This should make sense now, I hope. Look at the definition of a horizontal asymptote. The line y equals b, like that, is a horizontal asymptote of the graph of the function f of x if either the limit as we go to the right is b or the limit as we go left is b. Either one. It's not an and thing. This one goes left, it goes to q. But if it had gone, if we had called that, it wasn't called a b, but if it had gone to settled on a b, then it could be either one of those. So in this case, we have a horizontal. In this case right here, we have a horizontal asymptote but b, and a horizontal asymptote but q. And here we have a horizontal asymptote but 0. because the limits at infinity settle on those values. Not too hard, I don't think. That's our definition of a horizontal asymptote. We never actually defined it before, we just said it's just a line of approach. Now we've defined it with limits. So I can see how excited you are.
Yeah. Stuff.
Example 1 says, use the graphs and tables to find the limit at infinity of f of x and as we approach negative infinity of f of x, and identify all horizontal asymptotes of x over the square root of x squared plus 1. So it's a different function. We find the limit as x goes to infinity of x over the square root of x squared plus 1. Did I get that right?
Yeah.
We're going to try to find out what that is, and we're going to do this one as well. The limit as x goes left of x over the square root of x squared plus 1 equals 0. Okay? And I want you to think about this with me for a minute before we actually try to graph it or use tables. That's what he says to do, but I want you to think about it, what would happen. I want you to think about it in your head. Take a look at this function right here. And let's say that x was 4. Then you would have 4 over the square root of 17. Right? And I don't know what that is, and I really don't care, because 4 is not very big. I'm trying to get to infinity. So I'm going to consider something really big, like 1,000. Oh, wait a minute. I do want to go back to 4. Hang on a minute. This was 4 here. This was the square root of 17. Isn't the square root of 17 a little bit more than 4? Yeah? So I have 4 over something a bit more than 4. Let's take 100. Put 100 up here. The square of 100 is, anybody know? 10,000 and 1. What's the square root of 10,000 and 1? Check it out. What's the square root of 10,000 and 1? Not much, but a little bit more than 100, right? Okay. So if we made this 1,000,000, and we took 1,000,000 squared and added 1 and square rooted it, we'd get pretty darn close to 1,000,000. And it would be even closer yet. So a number over itself is 1. That is this limit. I don't know why I wrote that. That's just a habit. Sorry. Shouldn't have wrote that. What do you suppose happens if I let this be negative 1,000,000, and this be positive 1,000,000? Yeah. You can check that out pretty quickly with the graph or on your calculator. It will approach 1 and negative 1 pretty quickly. And it'll look like this. So that this is not B and Q, this is 1 and negative 1. That's what it's going to look like. Okay. So quite often, if you will just take a moment and stop and not try one of these things, just ask yourself, what is that fraction approaching if x is really, really, really big? Usually tell you what you're headed for. Then you can verify it with graphs and tables if you want, but I want you to get used to thinking about limits by plugging some things in for yourself and see what you think happens. Okay, I want you to look example 2 now. Sandwich theorem revisited. Page 71. Notice what we're limiting now. We're going to go the limit as x approaches infinity. That means we're going to go right. We're not going to go left. We're just going to go right, and that's it. For a function which is sine x over x. What do we know that limit to be? Really?
Not as we know.
What limit do we know dealing with that function that is 1?
As it approaches 0.
As it approaches 0. Pay attention to where x is headed. You can't just look at sine x over x, see the limit there and go, oh, that's 1. I know that's 1. No. That's the limit as x approaches 0 of that function. We're not approaching 0 today. Right now, anyway. We're infinity. And look at the graph that they have to the left of example 2. You see there, and they've stretched, take a look at the y-axis that they have there. The y-axis, you understand, I think you learned this from the pre-calc book. Down here, it'll tell you what the window is, window range. So look at that window range. Can you see that we're still convinced that as it approaches 0, that the value is 1? But we're not interested in what happens at 0. We're interested in what happens way the heck out there. And you can only see a little bit of that because it's only going from negative 4 pi to 4 pi. which is about 24. But I think you can get an idea that it is going like this. It's coming down, goes up, and it comes, but it doesn't come down quite as far. It goes up, and it just wiggling on out there until it actually approaches zero. Because the deviations from the x-axis get smaller and smaller and smaller. So this is approaching zero, even though it periodically, expectedly, goes up, and then comes back down below the x-axis and goes up above and back below and up above. And that's the sine doing that to it. But like I said, the deviations from the x are getting smaller and smaller and smaller as you go out. And so it's not really settling like an asymptote, but we will still call it that because it is settling on zero as it wiggles around, going out there. You with me? Okay, we'll still call it an asymptote, a horizontal one. What's that?
Nothing, I just said I was gonna call it the wiggly asymptote.
I'm a wiggly graph approaching a straight asymptote.
Okay.
Right. But again, I want you to consider this function that we're talking about. This is the sine of x over x. And I want you to consider what happens as we let x get really, really, really large. What is the sine of x always trapped in between?
Negative 1, 0, 1. Or negative 1, 1.
Negative 1 and 1, which means it never gets very big. This is not trapped at all. You got something that's really small, like between negative 1 and 1, like a half, or a negative half, or a negative 0.9, or something like that. And you divide it by 1,000,000. Isn't that?
That's pretty close to zero.
He's stuck. He's not. So when your denominator continues to get big without bound, your denominator is stuck some way or another, the fraction goes to zero. So that's a reasoning way of understanding that that thing's going to zero as well. If you were to use your table aspect of your calculator, and the way they have to the left of example 2, you can see that the y values are getting pretty darn tiny. They're changing in sign all the time. That doesn't matter. They're getting tiny, and you can tell that because at around 600, it says 7.4 e negative 5. And remember, e is pronounced times 10 to the. So that is really 0.0000745, or just 74. It's pretty tiny. And it's getting tinier as you go out, okay? So that was exciting, but what I'm trying to get to you here is ask yourself, if you're limiting it at infinity like this, whether it's left or right, in this case it's right, ask yourself what happens if x is a big number. What's it getting close to? Okay. I want you to look at Theorem 5, because it looks an awful lot like the theorem we looked at the other day, page 71. But notice the difference between the theorems. If you want to go back there and look, I can compare them, because the two boxes at first glance look almost exactly alike. And those properties are found on page 61. So 61 and 71. But the main difference is that our limits that we're looking at today go to positive or negative infinity and give you an L, that's an asymptote, or an M. And over here, we were approaching a particular x value, some specific x value. Here, we're letting x go out where we can't imagine it anymore. But the same rules apply. Look at the way the rules compare. The sum rule says if you add f and g, add L and M. Difference rule says if you're going to subtract, same thing. Same thing is true with f over g, so long as m is not 0, that limit is not 0. So they're exactly alike, except what we're approaching. That can make all the difference in the world. Third page. This is how it makes a difference with infinity. The reason why infinity is difficult to deal with, and even it's difficult for those properties to be of any help, you'll see here really quickly. I've got 5x plus sine x over x. And I'm just going to go out to positive infinity on this. Is that what they do, or is it positive or negative?
It's just positive.
It's just positive. So we're just going out to the right on this thing. So what we do, trying to apply those properties, we remember that if you've got a monomial in denominator, you can divide it into both separately, and you get these two functions, f of x over x plus sine x over x. And according to the properties, we can limit both of those as x goes to infinity separately. Well, this one can be simplified, this particular one, for considering it separately. That's just 5, right? And the limit as x approaches infinity of sine x over x is, what do we decide? 0? So the limit is 5? Yeah? Okay, so that one worked out pretty well. Besides that, think about this. You got a really huge number here, plus something tiny, divided by this number here. That's 5 over. This is insignificant. This part right here, this part doesn't really matter. This is 5x over x because this doesn't matter the farther out you go, the less it matters because it's tiny. So you get 5x over x anyway. That's another way to think about it. So that one worked out pretty well.
And what does a 5 mean? That's a limit?
It means that's an asymptote for this function. A horizontal asymptote for this function. What's that?
It's like the line 5?
Yes, y equals 5.
Okay.
That means that's what the y values are getting close to. That's what we're asking. Where are the y values going as x get large? And in this case, the y values are approaching 5. You can check it out if you want with your grapher. Let x go out a ways. Let's try it on another one. We're going to do exploration 5 and try it on some other ones. Example 1 says, let f of x be 5x plus sine x and g of x be x. All right, talking about the same thing again. So they're asking us to consider it a different way and see what happens. 5x plus sine x over x. So instead of doing this, instead of doing what the algebra, what instinctively tells me to do is to put this under there and put this under there and see what happens. They're asking us to consider this as f of x on top over g of x. Wasn't that one of our properties? Couldn't we consider it that way? Yeah. And so then they're saying that we could take the limit as x approaches infinity of 5x plus sine x and divide that by the limit as x goes to infinity of x. So if I consider this as a single function and I limit that one, that's going to be huge plus a little bit, so I get infinity. And this is going to be huge, but not as huge as that. That's still infinity. And what is infinity and divided by infinity? It's not 1 because it's not the same size as infinity.
Infinity.
And so we can't determine it. It's a big fat question mark. This will not lead you to an L over M. L and M has to be actual numbers, not some infinite thing. They have to be real live numbers, L and M. And they were over here. This limit was 5 and this limit was 0. Those are nice, neat numbers. We're able to add them together when we chose to add. Here, when we chose to think of this as a function and this is a function, and we divide and take each limit separately, we get nothing that we can depend on.
I have a question. How come the limit as x goes to infinity of 5x plus sine x, how come that's infinity?
Because it proves.
Because it's 5 times something extremely large plus almost nothing. This is going to infinity. This is not contributing anything.
Okay.
This is going to infinity also, but not as big as infinity as this one. We don't talk about sizes of infinity.
Oh,
Infinity is
so pretty much
infinity.
it just doesn't have any asymptotes.
Yeah, well, this doesn't allow us to discover any asymptotes. This did with the very same function, but we consider this one as an addition of 2 functions that actually have real live numerical limits. This one, we considered it as one function divided by another and tried the properties in that table and discovered that we ended up taking a limit of the numerator and a limit of the denominator, got infinity over infinity, which is completely inconclusive. So you're going, well, which one do you do? And the answer is the one that works. You go, how do you decide that? Because you keep trying. If you try this first and it doesn't work, try something else. If that doesn't work, grab your calculator, see if you can figure it out. Okay, take a look at number 2 in the exploration. This one says, let f of x equal sine x and g of x, sine squared x and g of x be cosine squared x. That seems like that's a leading thing. F of x equals sine squared, g of x, cosine squared. That's what they're asking us to consider. It says describe the behavior of f and g as x goes to infinity. Okay, so we're going to consider them separately. Anybody can tell me what the limit is of sine x? limit as x goes to infinity of f of x is what? What does it settle on? What does the sine squared of x settle on as you go out farther and farther and farther and farther? It doesn't. Check it out. Because it's sine squared, it's going to stay above the x-axis because you're always squaring it positive. So instead of having this go like this, it's just going to go like this. But still, it just keeps going up just as high every time it reaches a peak and comes down just to the x-axis every time, and it never does settle. How about the cosine? Same thing. So according to our properties, you can't take the limit as x squared, I'm sorry, as x goes to, not x squared, as x goes to infinity of f of x plus g of x, because that would be, we don't know, plus we don't know. However, we know what this is.
One.
It's 1.
Yes.
It's one of the Pythagorean identities, but okay.
Identity.
So we say, if you guys can see this better, if I actually replace these, because this is something you're familiar with. Not only does it approach 1, this is 1 all the time. I don't care where you go with it, it's going to be 1. So its limit, f of x plus g of x, is 1, but not by those crazy properties we just did. Because the limit of this one and the limit of this one cannot be determined, so adding them together can't be determined using the properties. But we know what it is. Again, another way. So you got to consider different options. Take a look at example 3. Natural log of 2x is one of our functions, and the natural log of x plus 1. So f of x, read it to me, please. What is it? Natural log of what? 2x, and g is what?
Natural log of x plus 1.
Okay, so what they want us to do in this one is to do a difference. We want to find the limit of the difference of f minus x. So take the limit, x goes to infinity of natural log of 2x minus the natural log of x plus 1 by, well, actually, this is what they want us to do. They want us to find this limit by doing this, limiting each one. So we're taking the limit of this one and subtracting the limit of this one, because that's what the properties tell us we should do. So, anybody have any idea what the natural log even looks like? Remember what it looks like? It goes like this. It hugs the y-axis way down here, and then it crosses at 1. This one will cross a slightly different place because of that too. But anyway, this is the basic shape. And it continues to go out like this, and it appears to flatten, but it never flattens entirely. I don't care where you go out farther, you go out here on this x, you go up to the log. If you go out a little bit farther, you'll have to go up a little bit higher. This thing continues to climb forever. It just doesn't climb very fast. So the limit as x approaches infinity is infinity, because this thing keeps going up, 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 up. It never settles, right? Same thing is true of this log. It's just been transformed a little bit. It's moved left 1, but it's still going to have the same behavior as x goes to infinity. So that's infinity, which leads us to no conclusion. But let's see what happens if we do this. See if we can remember limit as x approaches infinity of the natural log of 2x minus the natural log of x plus 1. So now we're combining them together and trying to simplify this, much like we did over here.
Wait, why are we subtracting just the two functions?
Because it tells us to.
Yeah.
In part 3 of exploration, it says find f minus g. The limit is f of f minus g. And I'm saying if we tried to apply the properties and find the limit of this f and the limit of g and then subtract the two limits would lead us nowhere. So now I'm considering doing it this way. And can anybody tell me how this function simplifies?
Because the difference or logarithms thing.
Can do what?
You can like take the 2x and then divide it by x plus 1.
Like this?
Yes.
Does that seem familiar, people?
Oh, yeah.
Log of a difference is a single log of a quotient, remember?
Yeah.
That's a property of logarithms. So this is what I'm limiting.
use your imagining skills again. If I put 100,000 in here and 100,000 in here, what's that getting closer to? 2? Do you see that it gets closer to 2? Because this would be 200,000 and this would be virtually 100,000. And the bigger you get, the bigger your x gets, the closer this gets to 2 over 1, no matter what you're plugging in, right? Because the 1 becomes less and less and less significant. So we end up with 2x over x, basically, in the limit out there. And the natural log of 2 is a nice, neat, irrational, but asymptotic number. This is the asymptote. By going about it a different way, by not applying the properties.
So you're saying that like,
So the limit as x goes to infinity is the natural log of 2.
For this function, for the difference of these two functions, yes. If you check it out, you'll see it. You type the equation y equals natural log 2 and y equals natural log 2, y equals natural log 2 minus natural log x plus 1, and you will see that as it goes out, it will approach that line. But this didn't tell us that. So I guess what I'm saying is what they're asking you in number 4. It says, based on parts 1 through 3, what advice might you give about applying Theorem 5?
Just graph it. It's good.
You guys depend way too much on those calculators. What advice can you give about applying the properties when we approach infinity? They're pretty useless.
Yeah.
That's the advice. Come up with another way. Apply your algebra skills. Apply your trig skills that you know. They will serve you better most of the time than these properties. Now, the properties served us well once. But I erased it right here. Remember when we took the x into the one, x into the other, we found the limits, and we said 5. That works one time. But all the author's trying to demonstrate here is, well, those properties hold. As far as being useful, they aren't very. You might be able to use them now and then. But if they don't work, if the properties don't work, you got to think about another way. Okay. And again, I don't feel like the author does a really great job here. We're going to switch gears here. He makes a big, bold statement, but it's hard to make it switch, so I'm going to try to drill it into your minds. We've been talking about letting x go way the heck out to the right or way out to the left and asking ourselves, what's y doing as that happens? Now we got to switch gears. Now we are going to approach, we're going to take limits as x approaches some actual value on the x-axis, some real number. Not way the heck out there, just some number someplace. Because that's what it says. It says infinite limits as x approaches a. And you're going, what? We're not going to infinity. And you're right, we're not. But you got to make a real switch in your mind about the concepts we're about to discuss.
Isn't that kind of what we did like in 2.1?
Yes, but generally when we limited it at a value, there was a y value that went with it. We are going to now approach a specific x value, and the y values are going to go to infinity rather than settle on something. Okay, so you see right down there, a definition just right there as we begin this stuff. It says if we approach a specific value of a real live number, we're getting closer and closer to x is getting closer and closer and closer to that number. If the y values as we get closer go to infinity or negative infinity, now we have a vertical asymptote. Does that make any sense? Okay. So let's go back to this because this is the classic. It's got both vertical and horizontal asymptotes that are in nice, neat places. So if I consider the function 1 over x, I have a graph that looks like this, sort of, okay? And this is also an asymptote, which we have not discussed yet. This was the asymptote we've been discussing horizontal ones up to this point. So now we're saying this, if I take the limit of this function as x approaches 0, a nice, neat, real, live number for x of this function, I get what?
Divided by 0 error.
What?
Divided by 0 error.
Yeah, if you actually let it arrive at 0, you get it divided by 0 error. The question is this is asking what happens as we get close to 0.
Depends on if you're going to the right or the left.
Exactly. Now what is it?
Infinity.
Infinity, yep. And if I go like this, the limit as x approaches that same zero, but coming in from the left side, we get
Negative.
negative infinity. So what is the limit? What is this limit then?
It does not exist.
Does not exist because they have to go be approaching the same thing to write anything down. You with me there? But notice that this isn't going to infinity, but the result is. That's how we've switched gears. We were going way out to the right and settling on a number for horizontal. This would have been a number, hopefully, like natural log of 2. But now we're approaching a number and we get infinity. Now we're talking about asymptotes that are vertical. Does that make good sense? Okay, so try to distinguish those two limit terms in your mind. Okay, let's see. The next one says, find the vertical asymptotes of f of x equals 1 over x squared. What does that look like? 1 over x squared. If x is a negative number, then when you square it, it's positive, right? Which what this does is takes this graph and flips it up over here on the negative side. So we don't get this branch anymore. We get a branch like this. And this isn't quite the same shape, but we're not interested in the shape. We're interested in its limits. So what is this one? Is this still true? That's still true. What is this one?
Infinity.
Also positive.
What is this one?
Infinity.
Yes. You may actually say equals infinity here because that's both headed in the same direction. Okay? Because they're both, even though that's not a number, they're both headed in the same direction. You may actually say that limit is infinity. But you can't say that about 1 over x. Okay? So take a look at example 5 then. Example 5 says the graph of f of x equals tangent x, which is sine x over cosine, has infinitely many vertical asymptotes. You knew that because you know how the graph looks like. Hopefully you remember. One at each point where the cosine is 0, because that causes division by 0, so there's an asymptote there. If a is an odd multiple of pi halves, if a is an odd multiple of pi halves. So we got a whole bunch now, and I'm talking about a tangent curve. I'm not going to draw it up here. But we know that odd multiples of pi halves, every time you run into an x value that is one of those, you get an asymptote. So what I'm asking is, what is the limit as x approaches one of those odd multiples of pi halves? So that's our A of tangent x. Can you imagine what the limit is at one of these asymptotes?
Depends on what's going from.
What's that?
Depends on what side it comes from.
Yeah, it does, depending on what side it comes from. So if I don't consider what side it comes from, knowing what you know about the tangent curve, how would you answer this question without a plus or minus on it?
Does not exist.
Does not exist. Because, and then I want to consider from left and right. So what's the limit? I'm going to call this A. What's the limit as x approaches A from the left of any of these tangent branches?
Positive infinity.
Is it positive infinity?
Yeah.
If you come in towards one of those asymptotes from the left on our tangent branch,
Oh, yeah.
positive infinity. Because, and I will draw this a little bit. This is an asymptote here and one over here. The tangent comes in like that. And so as we're coming in towards this asymptote from the left, we get positive infinity. If we come in towards one of these other asymptotes, and there's millions of them, from the right, you get negative infinity. Which is why this doesn't exist. Okay? We good? Not too bad. Now I want to talk to you, we have to switch gears again. Right there in the middle of page 73 where it says end behavior. I want you to, without actually graphing, I want you to look at those two graphs on the left of example 6 and notice the difference in the window size. Yeah, goodness is right. If you were to do that in your calculator, what it says there with the function we're considering, you would get the same thing. What I'm saying is that lower graph actually has two graphs on it. That lower graph that you're looking at has the blue one and the black one from above, but with an enormous window. So notice that the x's got 10 times bigger, but the y's got 100,000 times bigger. And the differences in the blue and the black, as we let the y's get huge, became so insignificant, your calculator could not distinguish them anymore. Okay? That's an investigation of end behavior. It means as x goes out farther and farther and farther and farther, what we notice is, as x goes farther, we keep looking up higher. As x goes farther and farther out, 10 times farther out than the original, the blue one has become the black one in the end behavior. As we go farther out and look up here at these branches, they virtually become the same thing. Even though they have small differences in here near the origin, as we go farther and farther out, they become the same function. And here's why. Look at the function we're graphing. Look at the blue one. Example 6 says this is the function we want to see. It's a nice polynomial, fourth degree, 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. G of x, the black one, is just 3x to the fourth. And here's why they become the same, because as x, think about this, as x gets bigger and bigger and bigger, the stuff following 3x to the fourth gets less and less and less significant. Because the 3x to the fourth term is outrunning all the others because he gets bigger faster as x gets bigger than all the others. And the farther out we go, the less significant they become. 3x to the fourth is outrunning the rest of them. His speed increases, or his size increases way more than the others with the same value of x as we go out. Okay, so in any polynomial, the end behavior model will be the leading term, because all the other terms become insignificant as we go out. Okay, they show that in the solution. I want you to look at it on page 73, near the very bottom of the page there. It says that limit, if we let 3x to the fourth, oh, this is an extremely important concept. I gotta spend more time on this. Hang on. All right, so f of x is, somebody read it again, 3x to the fourth what?
Minus 2x cubed plus 3x squared minus 5x plus 6.
Okay, so based on the discussion I just had, at least reasoning in your mind, we believe that the end behavior model for this, for f, is 3x to the fourth. And when I said it outruns it, or in other words, this function, this monster function here that's all spread out there, becomes 3x to the fourth as x gets large. Then what we need to then see if you can understand this as far as fractions go. If I take that 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6 and divide that by 3x to the fourth and take the limit as x goes huge, won't this fraction become 1?
Yeah.
Even though they're completely different functions. I mean, this one's huge here and this one we end up with this, all these getting outrun, we end up with 3x to the fourth over 3x to the fourth, and the difference is 1. So what I'm saying is this. If you take a function and you have chosen the correct end behavior model and divide them with the end behavior model that you suspect on the bottom. So this is a function, any function, and you look at it and you say, the end behavior model I believe is that. You put it down here and take the limit as x goes to infinity, you will always get 1.
Ah,
If your end behavior model choice is correct. And you're going, well, it's an easy choice. You're not always dealing with polynomials. You may have to pick and choose among things that are not polynomials that you're not so familiar with and test this. See if the function divided by what you have chosen is 1 when x is huge. And if it is, gets closer to it, then you've chosen the correct end behavior model, and that's how you test it. So if you turn the page, you get a definition, and it says just what I just said. A right end behavior model of f, g, I'm sorry, it starts up there. The function g is a right end behavior model for f, if and only if you put f over g and limit it at infinity, you get 1. Or limit it at negative infinity, you get 1. Okay? So you made the correct choice if you do that limit. So let's look at example 7. It says, find the end behavior model for, ooh, gross. F is not just a polynomial now, f is a rational function. But think about this with me, same sort of reasoning here. Look at the numerator. As x gets large, what's the numerator approaching?
2x
2x to the fifth, because it's polynomial. What's the denominator approaching?
3x squared.
3x squared. So our end behavior model is 2x to the fifth over 3x squared. And 2x to the fifth over 3x squared is 2/3 x cubed. That's your end behavior model. And if you were to take f, which is rational, that the whole monster fraction thingy, and divide it by this, as x gets large, you can check your tables out. It's a lot of typing, but you can check it this way. You better be approaching 1, and you will. What do you suppose is the end behavior model for b? Can you do that one more quickly now? It's this. I want you to recall from Algebra 2 and Pre-Calc, you remember that I told you that there were 3 tests that you had to run to figure out the horizontal asymptotes, which is what happens as the limit goes to infinity. That's what we're talking about. There were 3 things when you had one polynomial over another to decide where the asymptote was. And I made you learn them. I didn't tell you why it worked. We said, if the degree of the numerator is greater than the degree of the denominator, there won't be one. Because that itself is a cubed polynomial that goes up forever, never settles on anything. And that was when the denominator was bigger, the degree was bigger than the numerator. The numerator's degree was bigger than the denominator. In other words, we have an improper fraction among polynomials. There won't be a horizontal asymptote because it never settles. This is its end behavior model, and it's another polynomial. But when the degree of the numerator is equal to the degree of the denominator, you'll look to the leading coefficients. Isn't that just what we did in B? It settled on 2/5. Because the degree of the numerator is the same as the degree of the denominator, and the leading coefficients were 2/5. What do you suppose will happen if I have a polynomial like this? 3x to the third minus 2x plus 1 over 3x to 7x to the fourth minus 2x plus 8. What will it settle on? 3x to the third over 7x to the fourth, right? Equals 3 over 7x. What's this thingy going to as x gets huge? 0. And the degree of the numerator was less than the degree of the denominator, and we said y equals 0 is a horizontal asymptote in this case. And this is
How
why.
did we know it was 0
This is why.
from 3 over 7?
Because you put like a billion.
Because as x goes huge, you get something that's stuck over something that gets bigger and bigger and bigger, so the whole fraction goes to 0. That make sense?
3 over 7 billion.
And that's just what I told you would happen in pre-calc without giving you an explanation. This was smaller than this, so y equals 0 was a horizontal asymptote because the end behavior is 0. Okay, so now coming home to hopefully.
So if you're at a behavior thing model, would you do 3 over 7x or would you go with y equals 0?
The end behavior model is just 0. This end behavior model doesn't go to 0, it goes to infinity. It never settles on anything for horizontal asymptote. But that's because this was bigger than this. So this is the end behavior model, which itself is a polynomial. The end behavior model here is what happens, what's the model? Y equals 0. That's what it's going to. What's this one going to? This.
Okay.
You with me?
Yeah.
Okay. Now we're going to do one where we have to use that definition at the top of the page because it's going to be an unfamiliar thing that doesn't involve polynomials. Or maybe it does, but it also involves some transcendentals. Do you remember what a transcendental is? For our purposes, logs and trades. Here's what we wish to find the limit for. It says, let f of x equal x plus e to the negative x. And what we wish to do is figure out an end behavior model as we go right and as we go left. Now let's think about this. It's not going to be that hard to come up with one. This is f. What's going to happen as x gets huge? What's going to happen to this term as x gets huge?
It's going to get giant.
It's going to get huge. What's going to happen to this one as x gets huge? I'm talking about going to the right now. I'm talking about going right. That's a very important thing. We're going right. This is going to get huge positive, right? What's this going to do?
Small.
Wouldn't it be huge negative?
Well, does negative?
Because you have to flip that over the fraction because it's negative.
So it'd be like.
So it's the same as 1 over e to the x.
And as x gets huge, if 1 over e to the x, it goes to
0.
0.
Wait.
Come on, Ryan. Why?
Look with me. Do we all agree that this could be written this way?
Yeah.
Yeah.
Do you all agree that 2.718, which is what e is approximately, raised to a very, 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 very large number is a very, very, very large number?
Oh, but you got the one.
And 1 over it is very small. It's going to 0. So an end behavior model for this would be x, I would think. Because this one's going to nothing while this one goes to huge.
Okay.
That's not enough. That helps you analyze and decide what the end behavior model is. Now you have to do this. You have to do the limit as x approaches infinity of f of x over what you suspect is the end behavior model and show that that is 1. You have to show that. And it's not very hard. Because now you get to use your same skills again. And you would say, well, x plus e to the negative x, that limit over this one. Now we are using this function in this one. If I limit this one and I limit this one separately, I get x over x, which is 1. And I know that doesn't seem like much of a proof, but all the reasoning happens right here. We already did the reasoning to come up with this. But you have to show that if you limit f and you limit g at infinity, that you get 1. And this limit is x. We already discussed that. That's how we came up with it, because this is going to nothing. And this limit is x. I'm sorry, I lied. That's not what I meant to say. Let's see. How do they work this out? Because that isn't what I've got written there. Let's see. Oh, I see what they did. Yeah, this is better. Sorry, I screwed up. That happens once in a while, quite often. What we're going to do instead to verify this, because see, what I had was x and x, which would have been infinity over infinity, which is inconclusive. So I got to do something better with this. This is going to be x over x plus e to the negative x over x. And we're going to do it that way, like we did before with the 5 plus 0, remember? And take each one of these limits. This limit at infinity and this limit at infinity is going to be 1 plus 0, because this is going to 0 and this is going to infinity, and so this whole thing is going to 0. That's what I meant to do. Sorry. That's better. The other one failed. So I tried it one way by doing f over g, and it didn't work out, so now I had to try something new. I recognized it was wrong. So you have to try something new. All right, let's try and see if we can figure out a left-end behavior model for this same f. So now I'm going to say, what's the limit as x goes to a negative infinity of x plus e to the negative x over something we got to choose here. So now we got to come back to this, try to imagine what this thing looks like as we go way left. What's this thing going to approach as we go way to the left? Something really negative and big. So I'm going to say a negative big number. What's this going to approach as we go left? Well, let's take a look at it again. 1 over e to the x, but this is a negative number.
So it flips up.
Maybe it would be easier rather than do that is to look at this and say, if that's a negative number, this is e to the x.
So it's super big.
What?
It's big. So it's like
Yeah, it's going to be huge because this is a negative x now because our x's are negative. And so what we really have is a really negative, a negative really big number plus
super big.
a really big number. Which big is bigger? The one on the right, because this is an exponent. This is just getting big by increments. This is getting bigger, bigger, bigger. This one's getting bigger faster than this. Would you agree?
Yeah.
So this is going, so this one is taken over the value. It's outrunning this one. Would you agree with that?
I agree.
Then I suspect that the end behavior model for this is e to the negative x. You understand the analysis? Now we got to prove it. So I'm going to do the same thing I did before. I'm going to have x over e to the negative x plus e to the x, e to the negative x, over e to the negative x. We know what that limit's gonna be. What's this one gonna be? And remember, we are going to negative infinity. What's this limit gonna be?
It's gonna be pretty much zero.
Yeah, because if this is a negative number, this is e to a rather large positive number, but it's outrunning this one. So while this one is not a fixed number, it's still getting outrun by this, so this thing is still approaching zero. Therefore, this is the end behavior model as we go left. And therefore, this is the end behavior model as we go right. We've chosen the right one by showing that the limit was 1. That's the evidence.
Okay, so the one question I have is like, if you're going to the negative infinity, does that flip the sign on to e to the negative x or something?
It flips the sign on all the x's that you're plugging in. All your x's that you're plugging in are negative.
Oh, okay.
So I have a negative plug-in, which is
Does
positive.
that make that x on top of the e to the negative? Does that make it negative as well?
What?
Like that x above the e to the negative x in the final proof?
Here?
Yeah.
Yes, the plug-in here is also positive. So this is a negative number.
Okay, that's gonna be negative, okay.
Yeah, this will be negative. This will be positive, but it doesn't matter. This would be a negative fraction all the time, but that fraction is getting closer and closer to 0. It's still negative, but it's contributing less and less and less to this overall total, so we will say 0. And I guess we really ought to, if we're going to use that definition to do it, we ought to say, once we got this, we say, therefore, x is a right end behavior model. And we say here, therefore, e to the negative x is a left end behavior model. Okay, how we doing?
Time.
One more thing, and this will be quick. I want you to look at example 9. Notice that we are not doing sine x over x. We're doing the sine, just the sine of 1 over x. As x goes to infinity, I think it settles on 0. But here's what's cool. This is where it all kind of comes together a little bit here again. What I'm trying to tell you here is that the limit as x goes to infinity of f of x is the same thing as the limit as x goes to 0 from the right, because that's a positive infinity, so we're going to come in from the right, of f of 1 over x. So we reciprocate x, and now we can go to the different one. I mean, this went to infinity, this went to 0. So if I want to know the limit as x goes to infinity of sine 1 over x, I need to find the limit as x approaches 0 of the sine of x. Because the reciprocal of this thing that we're signing is this. And we all know what that is by direct substitution. And sure enough, the sine of 1 over x as it's asymptotically going out is this right here. And look at it, it's approaching 0. But sine x is actually 0 at 0, so it's the same limit. You can, by reciprocating x in your function, you can completely switch and reciprocate the limits.
So if there was 2x, it would be like 1 over 2x, like be how you find it.
Yes.
Mhm. Which is still the same.
Yeah.
I don't understand why you can substitute that x goes to on the positive side. I don't understand that.
Are you talking about here?
Yeah, no,
Here?
I don't understand how those are equivalent.
This is f of x. If you reciprocate x, in other words, you turn that over, when x was getting bigger here, we'll make this get just as small coming in because of the reciprocal thing. And so if you're trying to figure out this limit, you can't quite figure out what it is. It's quite possible for you to find f of 1 over x. Replace all your x's in f with 1 over x and take that limit as it goes to 0. And sometimes that'll be a little easier. This definitely was. Doesn't always work, but it's a nice thing to know. It's not a really handy thing, but like the sandwich theorem, it's pretty cool when you need it. That's just that little blurb right there, example 9. You'll have 1 or 2 of those to look at. Come back here and look at this. And the key is actually in the caption notation, which very seldom happens as well. Talks about f of x and f of 1 over x and changing the limits. So, all right, I can't believe I actually got that done, and just barely. There you go.
I'm